Hello everyone, today I'm going to present AppleE, Adaptive Planar Primate Learning from Evaluative feedback. This work is accomplished at Learning Agent Research Group at the University of Texas at Austin. So let's begin with the motivation of our work. So we want to deploy classical autonomous navigation system in different kinds of environments. However, whenever we put it into a new environment, we may need to tune its parameters. For example, for the DWA planner, which is the focus of this paper, it has a lot of parameters as a sampling-based method. For example, maximum velocity and angular velocity, the number of samples, and also how to score each sample. So if we keep using the same parameter, for example, a very large velocity and just a few samples, and if we put it into a highly cluttered environment, it of course will produce some suboptimal behavior or even cannot find a feasible solution. However, tuning those planners require expert knowledge. But even for non-experts, it's pretty trivial to tell whether the robot is doing well or not, and they can provide corresponding feedback easily. For example, here, when the robot is driving too slowly, or it cannot find a feasible solution and start recover behavior, people can just provide some feedback to help correct the robot. So this comes to our line of work, Apple Adaptive Planar Primate Learning. The goal of Apple is to use different human interactions to tune the parameter of navigation system. So when it produces the motor action from sensor data, we can optimize its performance. So far, we have work that use human demonstrations, human intervention, human evaluative feedback, and this is our work, and reinforcement learning. However, those methods doesn't need to work just on their own. Instead, we can use all of them to keep improving the performance of navigation stack. And this is in this new work. So how is AppleE different from previous work in this line? So first, of course, we use evaluative feedback. So compared to demonstration or intervention that require human to directly control the robot, collecting feedback doesn't need them to have the knowledge of driving robot, and as a result, it's much easier to collect. And then in the results, we will show why AppleE is outperforming AppleD and I. So how does AppleE work? At every time step, when human observing robot observation and action, it will provide corresponding feedback, and the feedback can be discrete, like good job, bad job, or a continuous scalar. And after that, we will collect the human observation, the parameter it has used, and corresponding human feedback. And then we will train a feedback predictor. The feedback predictor takes the observation and the parameter as input, and we will try to predict what kind of feedback that human will provide. And we can train it with the collective feedback so far. And we can use different laws for either discrete or continuous feedback. The third step is to train a parameter policy that will select the parameter based on current observation. So before we move into detail of that, one important assumption is that when human provides feedback, it not only considers current results, but also future consequences. For example, in here, the robot is going to leave this open space and entering a narrow corridor. In that case, we won't want it to drive as fast as possible. Instead, we want it to slow down so it will have a smooth transition. So you see here, we not only consider its current velocity, but also future consequence when providing feedback. Since current feedback already takes future into consideration, maximize current feedback is enough and also consider future results. So given that, here we show how to train a discrete or continuous parameter policy. For discrete parameter policy, it has a set of parameters it can select from. For the continuous one, it doesn't have such candidates, but it will select from a parameter space. For the discrete one, we use a DQ style architecture, where it will just iterate through all the parameters and select the one that has maximum expected feedback predicted by the feedback predictor. For the continuous one, we use a soft actor critic style architecture. So the critic is again the feedback predictor, and the actor will not only maximize this feedback, but it will also have a large policy entropy, so it will have better exploration. After seeing how FOE works, we begin with evaluative in simulated environment, where we can collect a lot of cheap simulated feedback. So for the robot, we use the clear path gecko and it uses LiDAR observation. For the feedback, we use a simulated one, and the value of that is just the velocity projection onto the local path. So when the robot is driving faster, the feedback is greater or better. And of course, that didn't take future results into consideration. And as a result, it can be suboptimal. And then the projection is a continuous value, but we can also discretize it into discrete feedback and also at different number of levels. For example, we can discrete it to binary feedback, like moving forward is good and not moving forward is bad. Also, we can try final resolution, like 3 levels. Moving up to 1 meter is okay. Moving up to more than 1 meter per second is good, or even 5 levels, 10 levels. And the feedback is provided at 1 hertz. For testing, we use this automatically generated environments of different difficulty levels. Among 300 environments, we use 250 for training and the remaining for testing. Also, we have a lot of questions want to answer in this simulated experiment. For example, how does different number of feedback levels will affect the performance? Of course, in theory, feedback of final resolution should produce better performance. Also, we want to compare FOE against different baselines. For example, the planar planar with default parameter, or FOI that use intervention, which is a richer impact modality where the human directly controls the robot, providing action. And also FOR, because FOR in theory has greatest complexity. Because reward is always optimal, the feedback can be suboptimal. Like simulated feedback is suboptimal, or human cannot pay attention all the time and provide suboptimal feedback. Also, to test the limit of FOE, we use a lot of feedback signals. But calm down. In future physical experiments, we will see FOE is still practical. Finally, we want to compare FOE versus in its continuous parameter policy versus its discrete parameter policy. We want to see, even with discrete feedback, will continuous policy still work well? So here are our results. We will compare discrete policy with continuous policy. And on the axis, we will vary the number of feedback levels. And more to the right, it has final resolution. And for the infinity, it means we use continuous feedback. On the y-axis, we compare FOE against baseline. So it shows the percentage of environment where FOE is significantly better on the top row or worse on the bottom row. For the significance, that means on each test environment, we have 20 runs for each method, and then we can compare t-tests on these 20 runs to see whether the performance difference is significant or not. We compare again the default planar, also FOI using intervention, and also FOR using reinforcement learning. So first, how does performance vary with feedback resolution? In theory, we expect using final resolution, will have better performance. But here we found actually using 3 levels of feedback already have a good performance. And that's a good news because 3 levels of feedback is still pretty easy and practical to that. And then compare against Apple I using intervention and also default, we can see Apple E is performing much better than them because it has more environments where it's performing better than environments it's performing worse. That's because Apple E is selecting parameter based on feedback, which is a performance measure. Instead, Apple I will select parameter based on whether current environment is similar to environment it's collected interventions. So it's selecting based on similarity. Of course, selecting based on performance, it makes more sense than based on similarity. And that's why Apple E is performing better. And finally, for the continuous policy versus discrete policy, we can see continuous policy is performing better. That's because it has larger complexity. That means it can select parameter from the parameter space rather than just a limited number of candidates. Here we also show Apple E is practical in physical or in real world. So again, we use the same robot, but we collect feedback from human supervisor. For simplicity, we just provide binary feedback and train discrete parameter policy. To further reduce the burden of subjects, we let them only provide bad feedback when it's necessary. Otherwise, we will assume the subject is providing good feedback. Finally, we just collect feedback for 30 minutes, which is not a long time. We train it in this environment and also test whether it will generalize in this environment. So among the training and testing environment, we can see Apple E both achieve this traversal time compared with default and Apple I that's using intervention. However, Apple R using reinforcement learning needs a lot of trial and error in this real world, so it's not practical and we leave it out. Finally, for the future work, since this work experiment is conducted during pandemic, we only test on one subject. If condition allows, we want to test on more subjects to see, for example, how little feedback is needed to train a relatively good Apple E policy. Also, we want to see whether Apple E will be robust with different expertise level of feedback criteria. Here it means whether the subject is more cautious or is more aggressive. Also, we want to improve how Apple E handle the feedback latency. Currently, there is no post-processing for that. By incorporating more of that, we would expect Apple E has better performance. That's all my presentation. And you can access our paper by scanning this QR code.